Okay, hello everyone. Today we will learn about negative binomial distribution and hypergeometric distribution. Okay, let's look at the negative binomial probability distribution. And the situation is like this. It models the number of trials y. It models the number of trials y in a sequence of independent and identically distributed Bernoulli trials before a specific number of success, and we denote it as R, a number of successes, and we write it as y follows negative binomial RP. And actually here, this is a bit more generalization of the geometric distribution. So in the geometric distribution, it's the number of trials before we get the first success. So it's in the geometric distribution, we get fails, and then at last we get success. This is geometric distribution. However, in the negative binomial distribution, we have r minus 1 number of success, r minus 1 number of success in the first place, and then we success in the last place. So if r equals 1, if we have r equals 1, this is actually same as geometric distribution. So NB 1P, actually this is same as geometric distribution with probability P. Okay, so let's define these two events, set A and B. The set A is the first y minus 1 trials, contains r minus 1 success, and the event B is trial y results in a success. So here in the set A, what it describes is that for the sample, we have uh, y number of letters, and for the first y minus 1 positions, there are y minus 1 number of letters. In each position we have fail or success, and the first y minus 1 position, we can have r minus 1 number of success. So the number of success, it is r minus 1, and for the last event it is success. That's the event B. Event B trial Y result in a success. This is for set B. This is for set A. And actually, to calculate the probability of Y equals Y, it is probability of intersection of A and B. And since these A and B are independent, because in a sequence of independent and identically distributed Bernoulli trials, so each of these events are independent Bernoulli trials. So set A is from the first y minus 1 Bernoulli trials, and set B is from the last Bernoulli trial. So these two sets A and B are independent. So this is probability of A times probability of B. And for the probability of A, we have y minus 1 success. So we have the probability for success is P. So P to R minus 1. Because we have r minus 1 number of success, and for the failure, we have y minus r number of failures. If you sum these two, it is y minus 1. So among all y minus 1 number of Bernoulli trials, we have r minus 1 success and y minus r number of failures, and the way we can choose success from this y minus 1 position, it is y minus 1 choose r minus 1. So this is the probability for event A, and the probability for event B. The probability for event B is just P. So this times this result in the following definition. So definition 3.9, a random variable y is said to have a negative binomial probability distribution if and only if here this This is what we just derived, and here y equals r r plus 1 dot dot dot. Yeah, this is negative binomial distribution. Let's look at the example 3.14. A geological study indicates that an exploratory oil well drilled in a particular region should strike oil with probability 0.2. Okay, so the probability of finding oil would be 0.2 from oil well drilled, and find the probability that the third oil strike comes on the fifth well drilled. So we tried to find oil 5 times, and then we want to find the probability that the third oil strike comes. So it follows a negative binomial distribution with 3 and probability 0.2. And we want to find the probability that the third oil strike comes on the fifth well drilled, so which is probability of y equals 5. Okay, and to calculate this negative binomial probability, we can use the definition. So there is 5 trials, and there is 4 choose 2. Success is from 4 choose 2. 4 choose 2, and we have 3 times of success and 2 times of failure. So this is the probability related to 3 times of success and 2 times of failure. So this results in this number. Okay. And let's move to theorem 3.9. If y is a random variable with a negative binomial distribution, find expected value of y and variance of y. Actually, for the proof of this, this can be directly derived using definition 3.4 and 3.5. However, these are a bit time consuming, and let's wait until we learn chapter 5. We can derive them with other skills that we learned from chapter 5. Okay, and just know that the expected value of y for negative binomial is r divided by p, and for variance of y is r times 1 minus p over p squared. Okay, let's move to example 3.15. Okay, a large stockpile of used pump contains 20% that are in need of repair. Okay, so 20% of pumps are in need of repair, and a maintenance worker is sent to the stockpile with 3 repair kits. So repairmen have 3 repair kits, and she selects pumps at random and tests them one at a time. If the pump works, she set it aside for future use. However, if the pump does not work, she uses one of her repair kits on it. Okay, so the repairman have 3 repair kit, and if the pumps work okay, she do not use the repair kit, and if pump does not work, she use her repair kit, and it's distinguished. Suppose that it takes 10 minutes to test a pump that is in working condition, and 30 minutes to test and repair a pump that does not work. Okay, so the time takes differently. For working in condition, it takes 10 minutes. For the pump that is not working, it takes 30 minutes. Find the mean and variance of the total time it takes the maintenance worker to use her 3 repair kits. Okay, so we want to find the probability of the expected time and variance of total time. Okay. And what would be the experiment here, and what would be the random variable that we can use? Here the worker repairman have 3 repair kits, and the process ends when she uses all the repair kits. So it is a sequence of Bernoulli trials for finding pumps, and the last event is the repairing the pump. So last event is success, and we will going to use 2 other repair kit in the middle. So it's kind of choosing 2 events from the here, and so this random variable y would follow negative binomial distribution. So let y the number of the trial on which the third non-functioning pump is found, and this y follows negative binomial with 3 and probability 0.2. And here, what we want to calculate is the total time. And for the time, for a given y, we have 3 number of pumps that need repair, and we have y minus 3 number of pumps that are working good. So for this working good condition, we need 10 minutes, and for the pump that needs repair, it takes 30 minutes. So the total time spent is the total time that we need is for the good pumps, for the functioning pumps, we need 10 minutes, and actually this is 3 for the pumps that is need for repair. We need 30 minutes. No zero here. Okay. Oh, again here no zero. Oh, here 60 is okay. 30 times 3 is 90, and here 10y minus 30 plus, so 60 is it's okay. Okay, and what we want to calculate is we want to find the mean and variance of the total time, and this is mean of the total time, and this is variance of the total time, and actually this is 10e y plus 60, and the ey is r over p, and here 3 over 0.2, and you can calculate this number. And for the variance, it is 100 times v variance of y, and this variance is rq p. And so if you plug in the number related to this, you will get the solution. 100 times variance of y, something. Try to solve this by yourself, and let's move on to next slide. The homework for section 3.6 are these. Section 3.7 is about hypergeometric probability distribution. And the situation is like this. Suppose a population consists of n times, r of which are successes. A random sample of n items is taken from the population, k of which are success. Okay, and suppose we have n number of items, and r of them are success. These are success, and we are sampling n number of events, n number of items, and k of which are success. So k of which are success. So this is the situation, and then the probability of k success, then the probability of k success follow the hypergeometric distribution, and we denote this as y follows hypergeometric n, r, and n. Okay, and about this, actually this is the total number of events is n choose n. So here's the population here. We have n number of items, and there are r number of success, and we are sampling n number of items. So we are sampling n numbers of items. So here we have n. The population is like 1, 2, 3, 4, dot 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 n, and we are randomly selecting n numbers from here, and here 1 to r, 1 to r, they are success, and r plus 1 to n, they are fail. And when we are sampling n numbers like 2, 5, 1, 11, 13, dot dot dot, we select n numbers, and among them we have k number of success. That number k that follows the hypergeometric distribution. So choosing n number, that is n choose n. So the total number of events for a simple event, the total number for that is n choose n, and for to have the k number of success, and actually here it is y. To have y number of success, it is r choose y. So the total number of success, we have r number, so it is r choose y times, and we have n minus r number of failure. So we have n minus r number of failure. So it the other is choosing n minus r choose n minus y, and so this is the probability for hypergeometric distribution. Okay, and let's look at example 3.16, an important problem encountered by personnel directors and others faced with the selection of the best in a finite set of elements is exemplified by the following scenario. From a group of 20 PhD engineers, 10 are randomly selected for employment. What is the probability that the 10 selected include all the 5 best engineers in the group of 20? Okay, so the total sample, we have 20 PhD students, and among them there's 5 number of success, 5 best engineers. Here we have 5 best engineers, and we are sampling 10. We are sampling 10 among them. And what would be the probability that all 5 best engineer included? So the random variable y would follow hypergeometric distribution. Okay, so random variable y would follow hypergeometric distribution. The total number is 20, and among them 5 are best engineers, 5 are success, and we are selecting 10 numbers from here. And what would be the probability? Py equals 5. What would be the probability of having all 5 best success inside of our selection? And the probability is actually we have 20 choose 10. All possible case is 20 choose 10, and among 15 we choose 5, and among 5 we choose all 5, and this is the probability that that we want to calculate. Okay. Okay, let's look at theorem 3.10. If y is a random variable with hypergeometric distribution, the mean and variance are these. This is theorem 3.10, and to prove this, expected value of y, actually this is equal to sum of y equals 0 to r, and the probability is n choose n. and we have n number of events, and among them all of them are success, and the other are failure, and we are choosing 10. No, not 10, small n number. We are choosing small n number of events. So the we have choose n number of events, and we have among r number of events, we are choosing y, and among n minus r number of events, we are choosing n minus y. Okay, and the expectation, by the definition of expectation, we want to calculate this, the y equals 0 to actually n, but if y is larger than r, it's not defined, so y equals 0 to r, this thing. And here actually this is very similar to derivation of binomial distribution. So here y equals 0 to r y, and choose n. Here we can write this as r factorial y factorial r minus y factorial, and choose r n minus y. Okay, here actually this y can be cancelled, so this can be this can be and choose n y minus 1 factorial, and this one can be r times r minus 1 factorial, and this part it's r minus y factorial. So we can move this r to outside, and n minus r, n minus y, and we can move r here, and also from this n this n, this is n factorial, n factorial, n minus n factorial. Okay, and here we can move one of n outside and one of small n outside, so this can be n minus 1 factorial times n minus 1 factorial, n minus small n factorial, and one of n go here, and so n n. And the inside of the summation, if y equals 0, then the inside part is 0, so we can write it as y equals 1 to r, and here we have r minus 1 factorial, y minus 1 factorial, r minus y factorial, and here n minus r, choose n minus y, and in here we have actually n minus 1, choose n minus 1. Actually it's n minus 1 factorial, n minus 1 factorial, n minus n factorial. Okay, and here let y minus 1 as z, and n minus 1 as n star, and r minus 1 as r star, and y minus 1 as okay, so if you write this way, then z equals 0 to r minus 1, which is r star, and if you rewrite this thing can be described as R star choose Z, and here N star choose N minus 1. Oh, and also let small n minus 1 as n star. Yeah, then n star minus G, and for this part, n star choose n star. And the inside of this is hypergeometric distribution. So this sum up as 1, and so this one is Rn over n. So this one proved. And for the variance part, it's similar but with far more complicated calculation like this. So I will skip here. For the relationship with binomial distribution and hypergeometric distribution, actually this is very interesting. This is the hypergeometric distribution, and if n goes to infinity with this condition holds, then it converges to binomial distribution. And we will also skip the proof of this, but we can intuitively understand the situation. So hypergeometric distribution, NRN, it converges to binomial distribution NP. Okay, we can understand this situation by considering this example. This example is from the binomial distribution, and here suppose that 40% of large population of registered voters favor candidate Jones. A random sample of n 10 voters will be selected, and y, the number of favoring Jones, is to be observed. Does this experiment meet the requirements of a binomial experiment? And for a large population, we can think of that this approximately follows binomial distribution because of these. So in here, we say that the random variable y follows binomial distribution with 10 and 0.4. However, if we change the problem this way, suppose that we have 20 population. Instead of this large population, if we only have 20 population and 40% of them are favoring candidate Jones, which is 8 voters favor candidate Jones, then what would be the probability y distribution of y? So y is the number of people favoring Jones. If this is the case, then it would follow the hypergeometric distribution. So y is following hypergeometric distribution because in this case we have 20 number of population, and among them 8 of them favor candidate Jones, and we are choosing 10 among so 10 voters, and so this is hypergeometric distribution. And in this case, if we make this population getting larger and larger, if we increase this number and also we increase this number with the restriction that n over r equals p, which is this one, then this problem converges to this problem, example 3.6 case. And so we can intuitively understand that hypergeometric distribution converges to binomial distribution when the n goes large. Okay. Thank you and see you next week.